Hello and welcome to the Meteorologist Deep Dive, our weekly in-depth look at all matters meteorological, exclusive to our YouTube channel. So if you are not already subscribed to our YouTube channel, please do hit that bell icon and the subscribe icon so that you never miss one of these when we upload them. And feel free to send us your comments. We love reading them. And feel free to share the love as well with many others who like these more in-depth looks at the weather and climate. Now, often we talk about current weather topics in this deep dive, but I've had a look around and, well, the UK weather at the moment is changeable, but not particularly exciting. I'll tell you what is exciting, though. Temperature scales. So in this week's deep dive, I'm going to be taking an in-depth look at temperature scales. Celsius, Fahrenheit, Kelvin. How many can you name? There are others. And I know what you're thinking. 20 minutes on temperature scales? It's not long enough. Well, let's see how we get on. And before we cover temperature scales, actually, I wanted to do a quick history lesson and look at, well, how we started measuring temperature in the first place, because you have to go all the way back to ancient Greek. And the first recorded thermometer-like device was from Philo of Byzantium back in ancient Greece, and it was something like this. This is a schematic of what he used. And it basically shows this bulb of air here and this tube of air going into this pot of water. And as the sun heated up the air, of course, the Greeks realized that the air expanded, and what they saw was the expanding air exerting pressure and pushing bubbles out. So they could tell when it was warming up, and equally, they could tell when it was cooling down, because then the air would contract in this bulb and you'd get lower pressure, and the air being sucked back into the bulb, basically, and the water, as a result, rising up into this tube. So this was a very early thermometer-like device. I say thermometer-like device. It wasn't technically a thermometer. It didn't have a meter. It didn't have a scale. So there was no temperature scale associated with this, so it's more accurately described as a thermoscope. Now, one person that people often associate with the early use of thermometers, of course, was Galileo. But actually, he also didn't really use thermometers. He was mucking about with thermoscopes again, things that look like this. This was a Galilean thermoscope, and it's a similar thing to the ancient Greeks, actually. What you've got here is this bulb containing air, and then this tube with air all the way down until you get into a vase of water with water extending up into this tube. And so just like the ancient Greeks, when the air in that bulb heated up, it's expanded, and the water actually dropped and came out of the tube and filled up the vase. And so you actually, unlike what you associate with today's thermometers, where you see the mercury or the alcohol or the ethanol rising in the tube, you saw the water level drop as it got warmer and then rise again as it got cooler. Couple of issues with these thermoscopes. As you can see, it's pretty big, not exactly portable. The reason it's so big is because the air expands only slightly as the air warms up, and so it needs to be quite large to detect the movement of that air and water and the changes as the air warms up or cools down. So it has to be quite big. Also, it's affected by air pressure, so it's not particularly reliable. It would have a different reading when there's high pressure and low pressure, as well as high and low temperatures. So it's not ideal, really. Now, moving on to temperature scales. The first, or one of the first temperature scales in more modern times was this young chap on a horse. This was Ferdinando de' Medici. His father died in 1621, and he ended up being the Grand Duke of Tuscany at that young age, and he had a miserable time. He suffered from, a poor marriage to his first cousin, for starters, economic bleak times, and also the plague. back in the 17th century. So he had a pretty rough time, and it appears he found solace in making weather instruments, barometers, hygrometers and thermometers, which they could be called thermometers because he actually added a scale. And he invented a thermometer that had alcohol and also apparently urine in it, which was more reliable than air and water. So it could be a bit smaller, but smaller increments. And also it was properly sealed. He melted the glass at the bottom of the tube with the alcohol or urine in it. And as a result, it wasn't affected by changes in air pressure, so he could properly standardize it and he could put a scale on this device. So it was technically a thermometer. It wasn't the first scale ever invented for temperatures. Back in the ancient Greek period, this man, Claudius Galenus, he created a temperature scale using various bowls of water. Now, the middle one had 50% boiling water and 50% ice. And then either side of that, he put 4 different bowls with different increments of, or different proportions of boiling water and ice. So you've got basically, I don't know, 25% boiling water in this one, 75% ice, and then 100% ice, and so on. So you've got these different increments, which I guess counted as some kind of scale. But another scale was also devised, and this one I love. This one I've only just discovered. Newton's scale. Isaac Newton, more famous for apples falling on his head, came up with a temperature scale, and basically, it's quite subjective, admittedly. He put numbers, and I know it's difficult to read this on the screen, but he put numbers against just different phenomena. So we start off at the top, 0, the melting point of snow, and then 0, 1, 2, that's the temperature of the air in winter. 2, 3 and 4 is the temperature of the air in spring. Up to 6, you've got the heat of the air in the summer. 6 is the heat at midday about the month of July. So I don't know whether you're familiar with British summers or not, but you know, it does tend to vary a lot at midday in July in this country. 12 was the greatest heat which the thermometer takes up in contact with the human body. More on that in a moment, actually. 14, or is it 17? That's my favourite. The heat of a bath, which one can endure for some time when the hand is dipped in and kept still. Who doesn't love a bath as hot as that? And then 20, the heat of a bath in which liquid wax slowly becomes solid and assumes transparency. And then you go all the way up and you've got 81 melting point of bismuth, 96 melting point of lead. So it's quite subjective, some of that, like the temperature of the air in the summer is, 4, 5 and 6. But there's a theme emerging, which is measuring a scale against the freezing points and the melting points of various things. And actually, someone who continued that theme was a Danish astronomer called Romer. And he, as we said, by this stage, this is the 17th century or the early part of the 18th century, and there were lots of people inventing thermometers, and there were lots of people putting scales on these thermometers, but they were all different scales. So this chap, he was the first to kind of standardize it and come up with a scale that is, well, the sort of beginnings of what we use in some places around the world today. His scale took the freezing point or the melting point of a mixture of salt, water and ice, so kind of like a briny, slushy mixture, and he set that to 0 on his scale. And then he set, because 60 was a really important number in astronomy, and of course clocks and so on, so he set the boiling point of water at 60, and then that made 7.5 the melting point of normal water, non-salty water. So that was his scale. He devised it while he was stuck at home with a broken leg, by the way. He had nothing better to do. But that scale set the foundations for a slightly more familiar scale, which is the Fahrenheit scale. And this is Daniel Gabriel Fahrenheit. Crazy life story. he was born in 1686 in Gdansk, and his parents died when he was 15 from eating poisonous mushrooms. He then got sent to Amsterdam to work as a bookkeeper, but he hated it, so he ran away and became a glassblower instead. Much more fun, right? And he spent his time making thermometers and barometers and so on. Now, he was the first to make a mercury thermometer, which can measure the temperature much more accurately than the previous sort of alcohol and air and water thermometers and so on. And he liked Romer's scale, but he didn't like the fractions, so he took 7.5 and changed it to 8 for the melting point of water. But then, because his thermometers were more accurate, they could measure in smaller increments, he decided to multiply the whole thing by 4. So 8 times 4 is 32. That's where the Fahrenheit scale gets its 32 for the freezing point, melting point of water from. And then he added 180 to that to get the boiling point of water, so 212. And he also decided to set the temperature of the human body to 96. And he was able to calibrate all his thermometers by sticking them under his wife's armpits to make sure that they're all set to 96. So very important job for Fahrenheit's wife there. And his scale obviously is still used today in some parts of the world, most famously the US and US territories, also a number of Caribbean countries. And some countries, the countries here, by the way, in yellow are the countries that use Fahrenheit. There's a few spots here that are blue. They're the countries that use Celsius and Fahrenheit. All the other countries, green, they're the countries that use Celsius. So still used today, probably not still calibrated under his wife's armpits. Now, this is Anders Celsius. So we're getting on to the beginnings of what most of us use today. Swedish astronomer. A lot of astronomers actually involved in devising these temperature scales. He set the boiling point of water to 0 on his scale and the freezing point of water, or the melting point of water, to 100. I've not made a mistake there. You've not heard me incorrectly. The boiling point of water was 0 and the freezing or melting point of water was set to 100. The reason he did that was because he didn't want negative numbers during the Swedish winter. So if you had, say, a very cold morning in Sweden, it would be 110 and not -10. But after he died in 1744, his scale was reversed, and it was called the centigrade scale. And it was called the centigrade scale for many, many years, almost 200 years, until in 1948 it was internationally adopted as the standard for most countries around the world and renamed to honour Celsius. So renamed to the Celsius scale, and that's what we've got today, the Celsius scale. 0 degrees is the melting point of water, 100 degrees is the boiling point of water, the reverse in terms of what he originally came up with. Here's a scale or a diagram showing the comparison between Fahrenheit on the right, Celsius in the middle. You've got the different boiling points and room temperatures and so on, the different numbers. So 80 degrees approximate room temperature there for the Fahrenheit scale, 27 for the Celsius scale. The boiling point of mercury and so on. So it's pretty high for the boiling point of mercury. That's a reason why the thermometers often used mercury. Not so much these days because it is a toxic metal. But we've also got Kelvin here, of course. Kelvin is a relatively, when you look back at history, a relatively new scale, but of course this is the scientific unit, the international scientific unit for in terms of measuring temperature in a scientific way. So the Kelvin is set to 0 degrees for absolute 0. Basically, that's the temperature at which no particles move. So any temperature above that, as you add more heat, particles move faster and faster. And that's what temperature is. It's all about the kinetic energy of particles and so on, atoms and so on. So as the temperature increases, they move faster. But at absolute 0, they all come to a halt and don't exert any pressure. That's what absolute 0 is it doesn't really occur on the Earth unless, of course, you create it in a scientific lab. But it's very cold. It's minus 273.15 degrees Celsius. That's what absolute zero is. Lord Kelvin, who devised the scale, British Lord, he set it so that it was easy to convert to Celsius. So each degree of Kelvin goes up by the same degree as Celsius. All you have to do to convert Celsius to Kelvin is subtract or add 273.15 degrees. So that's Kelvin, and it's useful for scientific measurements because, of course, it starts at zero for absolute zero and then goes up in increments of degrees. And I like this. This is good. I don't know the original source for this, but it shows how these different scales affect us from 0 to 100. So Fahrenheit's actually a very useful scale for measuring the weather, admittedly, even though, you know, most countries don't use it, because you've got 0, it's really cold, 100, it's really hot. And the way I've heard some people describe it is that in between, it's kind of like a percentage of warmth. So 50, it's 50% hot, 50% cold, it's about right. Whereas 70, you're getting towards more warm than cold, so it's warming up. 90, it's really quite hot. Likewise, 10 would be mostly cold. Celsius, though, is, if Fahrenheit is how humans feel the weather, Celsius is how water feels the weather. So 0 is fairly cold outside, 100 degrees for humans, dead. But for water, it's the boiling point, of course. And then for Kelvin, 0 and 100, dead, dead, because, of course, both those temperatures are very, very, very cold. You're going from minus 273.15 to minus 173.15. That's how atoms feel the weather. That's how I've heard it explained. How humans feel the weather, how water feels the weather, how atoms feel the weather. So, little scientific joke there. Moving on to how we actually measure the temperature these days, of course. We keep thermometers in boxes like this, Stephenson's screens, named after Thomas Stephenson, who invented them. He was, I can't remember if it was the son or the father, one or the other, of Robert Louis Stevenson, of course, famous author. And he created these Stephenson screens, which basically shield thermometers from direct sunlight, but allow free-flowing air through. And thermometers, it's important that we measure the air temperature. So we're sampling the temperature of the air, but without the thermometer being heated up by direct sunlight. Because if they are being heated up by direct sunlight, they're measuring how hot the thermometer can become when it's sitting in direct sunlight. It's similar to how we experience temperatures and the weather outside. It's very unreliable, very subjective when we go outside, because our bodies are being heated up by direct sunlight if the sun's out, and our bodies then heat up and give off all this warmth, and we get this layer of warmth around us, and we end up feeling a lot hotter than the air temperature would make us feel in the absence of the sun. So you know how much cooler it is if you sit in the shade versus the sun. The actual air temperature doesn't vary that much because the air's flowing through the shade, it's flowing through the sun. It's ourselves that are feeling different if we sit in the shade versus sit in the sun. Sitting in the sun, we've got this layer of warmth around us that is making us feel a lot hotter than the air temperature would manage on its own. That's why we are not a very good thermometer ourselves. And of course, you've heard about the feels like temperature as well. It's another measure of temperature, or at least a way of expressing how the weather affects we humans. And the feels like temperature takes into account the speed of the wind as well as the temperature, and it's based on the fact that we're giving off heat, but the loss of heat from our bodies accelerates when it's windier, because the wind then takes that layer of heat away from our bodies, that skin surrounding us, and we feel colder as a result. And the feels like temperature is based on experiments that show the rate of heat loss for people in a wind tunnel, basically when they are standing still, or at least with a 3 mile per hour wind, I think, a walking speed kind of wind. and as the temperature lowers, versus the same temperature but with an increasing wind. So it is based on real experiments that they did on people in wind tunnels, based on varying strengths of wind and also varying temperatures. So they've come up with this scale that we use, that we can use in the winter. It's useful. Another way of thinking about how the temperature feels on human beings is, of course, heat stress, and also you might have heard of the wet bulb globe temperature. In those Stevenson screens, the thing I just showed you, we've got what's known as dry bulb thermometers. So they're just thermometers that sample dry air. But often we also have wet bulb thermometers. Wet bulb thermometers have a wet cloth on the end of them, and the wet bulb temperature that those wet bulb thermometers measure is the temperature of the air after you've evaporated water through it. And the temperature of the air when you evaporate water through it will often go down, will normally go down, unless the relative humidity is at 100%. So, you know, on a foggy day or whatever, it might be 100%. But normally, the temperature of the air goes down when you evaporate water through it, because the energy needed to evaporate water takes heat from the atmosphere. That's called latent heat, and reduces the temperature of the air surrounding that thermometer as a result. So if you've got this wet cloth, it's evaporating water, the air surrounding that wet bulb thermometer is going to reduce, and you get this wet bulb temperature. And that's useful for determining how much moisture is in the atmosphere, because the more moisture in the atmosphere, the less that thermometer will go down when you evaporate water through it. The reason for that is because evaporation will be slower, because you've already got plenty of moisture in the atmosphere. So we want to know what the humidity is, because that's another factor when you go outside, as well as the wind and the strength of the sun, on how the temperature feels, how the weather feels outside. And something that is really important when it's hot, particularly in countries in the tropics and so on, or for people that do jobs that are very strenuous, or for example, if you're in the military or something, then you need to know something called the wet bulb globe thermometer. And that's a measure of the humidity, the strength of the solar radiation, and the temperature outside. So it takes all those factors and comes up with a wet bulb globe thermometer. And what you've got on the screen there is a device that's measuring the temperature, the wet bulb temperature, so the water content of the atmosphere, and the black globe temperature. That's what this is, and that's measuring the strength of the radiation. So the wet bulb globe temperature is a formula taking from several readings, temperature, wet bulb temperature, and the black globe temperature, that take into account the humidity of the atmosphere and the strength of the solar radiation, so that it's possible to see how the heat outside is going to affect humans. But of course, going back to the original point, thermometers in a Stevenson screen aren't affected by humidity or by solar radiation, because they're not humans, they don't sweat, and they don't absorb heat from the sun. Well, they shouldn't do, they should just sample the air temperatures. Humans are not the best way of measuring temperature, of course. It varies as well on our own physical activity, what we're wearing, what we're used to. Is it colder today than it was yesterday? All of those factors matter when it comes to how it feels outside. And so the only way to get a consistent and reliable temperature reading is by taking a temperature reading from a Stevenson screen from a properly calibrated thermometer, or another way of doing it is by listening to the chirps of a cricket, because this fella, Amos Emerson Dolbear, American physicist and inventor, he discovered that crickets, I beg your pardon, chirp faster or slower depending on the air temperature outside, and he even came up with a formula. The number of cricket chirps in a minute minus 40, all divided by 4, plus 50 is the temperature in Fahrenheit. So that supposedly is a relatively reliable way of determining the temperature outside if you listen to the crickets. Although apparently it's only relevant to a certain species of cricket in North America, I think the snowy tree cricket or something like that. But crickets, if you don't have a thermometer, but if you do have a thermometer that's properly calibrated in the Stevenson screen, that's a much more reliable source for measuring the temperature than just guessing based on your own experiences outside. I hope that's been an interesting tour of temperature and scales and how we measure it all. But do let us know if you have any comments or questions or feedback, and we'll be back again with another deep dive next Tuesday. Thank you for watching. Bye-bye.